function, I chose to do a third degree polynomial over second degree polynomial. The function is x cubed minus 3x squared minus 10x plus 24 divided by x squared plus 2x minus 8. In order to deal with this function, we need to put the numerator and the denominator into factored form. So as you can see here, I factored the numerator by determining that x plus 3 is a factor using synthetic division, and then determining that the numerator is those factors. Now, to factor the denominator, it's a simple quadratic, so a one-step factor, and I determined that the function is x plus 3, x minus 4, x minus 2 over x plus 4, x minus 2. As you can see, that there's a common factor on the numerator as well as in the denominator, and anything divided by itself is equal to 1, so these factors cancel out, and a hole will occur on the graph at x cannot equal 2. So this produces the function x plus 3, x minus 4 over x plus 4, where x cannot equal 2. It's a second degree function over a first degree polynomial. Now the graph of this function looks like this, and as you can see at the point 2, the y value is undefined. That's where the hole exists. In order to determine the vertical asymptotes, it's whatever values of x make the denominator equal to 0, because when the denominator equals 0, the y values of the function are undefined. Now the only value of x that makes the denominator of this function equal to 0 is x equals -4. Plotted on the graph, this looks like a vertical line at -4, and the function will approach but never cross this vertical line. Because the degree of the numerator is exactly 1 higher than that of the denominator, an oblique asymptote will occur. In order to determine the oblique asymptote, I need to complete division between the numerator and the denominator. In order to do this, I use synthetic division, and I determine that the oblique asymptote occurs at y equals x minus 5 with a remainder of 8 over x plus 4. This oblique asymptote plotted on the graph looks like this linear line, and again, the function will approach it, but it won't actually cross the line. Now the function actually behaves like that linear line in extreme values of x, because the dividend is equal to the divisor times the quotient plus the remainder, which means the dividend over the divisor is the same thing as the divisor times the quotient plus the remainder over the divisor. This flows out to mean that the quotient is going to be the quotient plus the remainder over the divisor, and as extreme values of x occur, the remainder over the divisor will get increasingly close to 0, which means the function will behave more and more like exactly the quotient where the oblique asymptote exists. As you can see in the extreme values of x, that's x equals 1000, it behaves very similar to the oblique asymptote, but doesn't actually touch it. Now the roots occur when y equals 0, so the numerator of the function has to equal 0, and these roots occur at x equals -3 and x equals 4. Those are the roots of the quadratic in the numerator. A y-intercept occurs when x equals 0, so you sub 0 in as all values of x and determine that y equals -3. The domain of this function is directly influenced by the vertical asymptotes because those are the only values of x that it doesn't cross, so x is equal to real numbers such that x cannot equal -4. Turning points based on the graph on Desmos occur at essentially -1, -3, and -7, -15. And the range is directly dependent on these turning points because y is equal to real numbers such that y is either going to be less than -15 turning point or greater than the -3 turning point. So as you can see on the actual graph itself, all of these aspects plotted, you have your zeros at -3 and 4, your y-intercept at -3, and your turning points here at -1, -3, and here at -7, -15. Now areas of increase and decrease are essentially determined from this graph. As you can see, the function increases to this turning point here, decreases away from that turning point, decreases from the asymptote towards that turning point there, and then increases away into infinity. This is simply represented in interval notation. The end behavior of the function, again, can be determined from the graph. As you can see, when x approaches infinity, y is also going to approach infinity, and vice versa. When x approaches -infinity, y also approaches -infinity. Now the IROC of the function at 2 points, I chose x equals -3 and x equals 4 here and here. -3 should be occurring with a negative IROC because it's an area of decrease, and the IROC there is equal to -7.008, and at x is equal to 4, it should be a positive IROC because this is an area of increase, and using a following interval, it was determined that the IROC there was 0.875, which makes sense because that's a less steep slope than the IROC of this point here, and so it's positive IROC as the function increases that way.